Hello guys, today we are going to solve the sum example in the Matlab programming language using the script applications. Okay, and so this convenient or the whole the equations and the examples are related to the convolutional operation in programming language. Okay, first of all we need to give the clear all, close all and CSC. These are the predefined commands for for clearing the whole the data and closing all the figures, and the command history can be deleted using the CSC commands. Okay, firstly we need to build the 1D one-dimensional signal convolution. Okay, this is the first example. So in the first place we need to define the two discrete signals with the sampling frequency of the 100 and the total time duration for a given this fs, and so which means that we need to utilize the 4 times 100, which equals to the 400 values should be used in the convolution operation. Okay, and so we need to create the vector just like this one, 0 to 1 divided by fs. These are the step number in here, and until t. Okay. And so in order to convolve two signal, we need to define two signals. First of all, the signal one is a square wave active between the some period, for example 1 and 2 seconds in here. Okay, and so x1 should be created in here with the zeros and 1, and also we should give the length value in here just like this one, t. Okay, because we have the total duration which is given in the t variable, t vector. Okay, and so we need to assign the square wave for this signal. x1 can be conditioned with the t greater than equal to 2 and t smaller than equal to 3 must be assigned with the 1. Okay, we can assign any signal in the array structure of the MATLAB by using this notation. Okay, and so this condition is true, and then this variable or the indices are assigned with the 1 value. Secondly, we need to define the second signal in here just like this one, defined as desired signal, for example an impulse. Okay, or we can define the unit step or square wave. Okay, x2 can be defined with the zeros value 1, length of t. Okay, and so we have the 1 row value and we have the length of the t column value in here. Okay, and x2 can be conditioned with the t is greater than equal to 1 and t smaller than equal to 2 can be assigned with the 1, which is this is the square signal. Okay, so how can we calculate the convolution of this signal? This is important. First of all, we need to create the pre-allocate the convolution results in here. Okay, y should be assigned with the zeros value, but this the first row value is equal to the 1, but the convolution is the collection of these two signals, which means that we need to give the length x1 plus length x2 plus or minus 1. Okay, these are size for the for the y or the output signal in this discrete convolutional operation. Okay. Because we have a H signal and the input signal in here, just like this one. And then if we want to convolve this two signal in the discrete format, we need to create a double times array vector to what? To store the whole the values which is given in here. Okay. We have some specific function in the MATLAB, such as the con function, which is returning to the what? To our convolutional result. But if you want to perform the manual convolution, we need to build the nested for loop in here. For example, n is equal to the 1 to length y, because we need to create at each time to what? To convolution results in here, just like this one. And also we have a pattern or the impulse or the convolve function in here, apart from the what? The input signal. And so we need to also define k is equal to the 1 to length x1. Okay. and should be given in here. Okay. And so how can we calculate this value? For example, if n minus k plus 1 if greater than 0, which means that if you have the n is equal to the 1 and k is equal to the 1, and so at each time the k is convolved with the what? With the related index in here. But for example, f is equal to the 1 but the k is equal to the 5, which means that this cannot yield the convolution results in here, because to what? If we have this information in here, and then we cannot multiply in the what? In the discrete domain. And so we need to give this condition in here. Also we need to give this condition n minus k plus 1 smaller than equals to what? The length of x2, because we have a pattern, convolved signal in here, convolutional pattern up to what? Up to x2 signal. Okay. So we can give the n in here and yn at each time yn plus x1 k times x2 n minus k plus 1. Okay. We can calculate the whole convolution based on the what? Based on this information. This is important to know that, because if we want to implement this algorithm in the what? In the microcontroller structure or the C or C++ language for an embedded system, and so we need to give or write this convolutional algorithm with the nested loop structure. Okay. So these are the algorithm just given in here, just like this one. And so how can we visualize the whole results in here? Firstly, adjust time vector for the convolutional results in here. T con is equal to 0 and 1 fs, the r step number in here, and also length y should be given in here with the minus 1, and also we need to give the what? The fs. Okay. This is important because of this length y is the double times of the what? The x1 and x2, right? So how can we visualize the whole results in here? Figure subplot 3 1 1 and plot t x1 and title signal 1 x1, x label is the time sec, y label is the amplitude, and x lim should be limited with what? The 0 to t. Okay. And also subplot should be given in here just like this one, 0 1 2, and the second subplot in here just like this one. We can copy of all of these things in here, x2 and signal 2 and signal 2 sec amplitude, okay, and also subplot 313, okay, and we need to write the plot t cone comma y, okay, and title convolution results, which means that x1 and x2, okay, and x label time sec and y label amplitude, and x lim should be limited with the what, with the 0 to t value is the time limitation, and y lim should also be given in here just like this one, 0 to max t com. No, I'm sorry, this cannot be given in here. So if I run this code, and then we will have the arc convolution results just like this one, okay. For example, we have the x2 signal, x1 signal, and so after the 3 seconds we have the increasing pattern in here just like this one. For example, if we have, or if we don't have used this algorithm, instead of the max t cone in here just like this one, and so we have the 1 and we have 2 to 3 value in here just like this one, and so we can create the 3 to 105, okay. But just remember that this signal is 1 and the other signal is up to 1, but our convolutional result is 100. What's the meaning of this? It means that we have the fs signal in here just like this one is at 100, which means that at each iteration we can multiply, or the integral values creates to up to 100 values for this algorithm. So in order to normalize your signal, you should divide your signal with the division of the y divided by fs, okay. This is the normalized convolutional pattern in here, okay. So at each time we know that at a 3 we have the increased signal in here just like this one, and so up to 4 value in here, and then we will have to maximum value, which means that x1 and x2 is multiplied, or is covering the same area at these notations, okay. For example, if we have this information, and then we can create another pattern in here just like this one. We can define the new x2 signal in here. For example, like t at t is equal to 0, and so this is the impulse signal, okay. At this time we have the 2 to 3 value, we have 2 to 3 seconds at at amplitude values of these terms, and so this represents to the r signal notation. But in the impulse response we should not use the fs value because we don't have any iteration in here just like this one, and so 2 to 3 seconds are given in the amplitude of these terms, okay. This is important. So this is the first example related to our convolution study, and so also we can use the signal convolution in cone function. This is the predefined function which is given in the MATLAB, and so we can build or evaluate the performance of this function also in here. Okay, and so t min is 0, t max is 5, and after that we can define the time vector in here just like this one, the fs, for example 1000. This is a sampling frequency, and the t can be defined with what the t min 1 divided by fs, and t max can be given in here. Okay, and also we can define the t output value in here. Okay, t min 1 divided by fs and 2 times t max. Okay, because in the convolution integral we doubled to the what to the size of the r vector. Okay, firstly we can define the impulse response of ht, which is equal to minus exponential minus t. Okay, and so the h can be defined with what the x values in here minus t min value. Okay, because this is the standard operation for the what, for the initial condition. At this case we have the 0 value at the t min. We can remove these terms, but if we want to apply any other values, such as that, we can assign the t min is equals to 2, and then we should apply this algorithm in here just like this one. Okay, and also we can define the input signal. For example, the ut is equal to the 1. Okay, unit step function, and u assigns or created with the what, the ones and the length of t. Okay, and after that we can compute the convolution in here. Y is equals to what, the con hu. Okay, but we need to know that we should also give the what, the 1 divided by fs should be multiplied with this convolution operation, because it's a normalization form of the r signal. Okay, so we can visualize the whole results using the subplots 0 1 1 1, and plot t minus t min should be given in here because it's important. It scales the r output for the what, for the impulse response. Okay, so the title impulse response ht. Okay, and also x label time sec, and y label amplitude. Okay, and x lim should be given in the what, minus 5 to 10. Okay, this is time section, and grid one should be given in here. After that we should also define two input signal u. Okay, and this is the input signal. ut and time and sec and 5 minus 5 and 10 and this one. Okay, and so we can also copy after this term in here, the 3, and this must be equalized with what, the t output. Okay, and y, and this is the what, the output signal. At this case the dimension of the y is double time of the what, the template pattern and the input signal. Okay, so if I run this code, and then we will have these results in here. For example, if we have the exponential term, or if we have this kind of impulse response for a given system, and then if we apply the amplitude of this term, and then we will have to this kind of output in here, just like the first order dynamics of the R algorithms. Okay, and so the R algorithm is run or is okay with the what, with this notation. Or if we have this information, we can define, for example, the zeros value, or we can copy off these terms in here just like this one. We can apply the what, the ut is equals to the 0 at the 1, and so if I run this code, and then this is the impulse response of the our system, and so this system is given with the what, with this notation, but the output signal is equals with the what, with the impulse response, okay, or the R modeling impulse, okay. These are the example of the what, the convolution operation for the what, for our algorithms, okay. This is the 1D signal, and this is important. Just remember that if we have this information, and then we can convolve any signal for a given the template pattern of the system dynamic impulse response of the system. For example, the mass spring damper system, or the what, the RC circuit, and then we can generate the what, the our results in the what, in terms of the convolutional integral. We can calculate the output of these terms because we have the time scaling template function to generate this output, okay. What about the two-dimensional convolution? It's another important parameter for the what, for especially for the embedded system applications, okay. Firstly, we can define the simple 2D signal, such as the signal just like this one, the 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 and 21 22 23 24 25, okay. And after that we should define the averaging filter, which we call it the kernel, okay. In 2 dimension we can say that this is kernel, okay. Firstly we need to give the what, the kernel size in here just like this one, and so the kernel can be defined with the what, the ones, and kernel size, and kernel size divided by the what, the kernel size times kernel size, okay. The second operation, or the division operation, is directly related to the what, our normalization operation for averaging pattern, okay. So for the convolution results we should give the count to the signal and the kernel, okay. And after that we should visualize the whole results in here, subplot 1 to 1, okay. And image SE, the signal value in here, and title should be given the original signal in here, okay. And also color map should be given as the gray in here, just like this one. And color bar can be used as in here. Axis image, ensure the aspect ratio is the what, is 1 and 1, okay. And also we can define the subplot 1 2 2, okay. Image SC, the cone results must be given at this time, okay. And title after 2D convolution, okay. And color map should be assigned with the gray value, and color bar and axis image should be given in here, okay. After this operation we need to give that these values should be averaged due to the what? Due to convolution operation. Okay. But we have the some subplots. Okay. See, we have the black tones in here and up to what the white tones at this time, but after the convolution operation, and then we will average all the patterns in order to what? In order to distribute it equally at each space, just like this one. Okay. So we can easily apply this algorithm based on these informations. Okay. So the final example about the convolution operation is the mass spring damper system for a given unit step response. In every era of the system dynamics control theory or the digital signal processing, we can apply this unit step response to the what for a given system or the system equation. And so we can build this algorithm just like this one. T min is equals to 0, T max is equals to the 5, and we need to define the time vector in here with the sampling rate of the 1000s. And so the T min and 1 divided by Fs and T max should be given in here. Also, we need to give the T output value here, just like this one. T output in terms of what, the 2 times T max. Okay. So, what is the impulse response of the what of our mass spring damper system, just like this one? Firstly, we need to give the T absolute value in here, T minus T min, and H can be defined with the sqrt q dot times exponential T abs dot time sinus q dot time sqrt q dot times T absolute value dot times 9 divided by 4. Okay, these are the general pattern for a given what, the mass spring damper system. Okay, where it's coming from? It's coming from the what? If we have this mass spring damper system, we can take the Laplace transform of this system. For example, 1 divided by ms square plus cs plus k, right? And so if we apply the Dirac delta function in here, and then we will get what, the inverse Laplace transform of this general pattern for a given Dirac delta function. And so this Dirac delta function gives us this solution in here. Okay. And also we can define the input signal just like this one. U is the ones length of t. Okay, after that we should give the y convolution h and u times 1 divided by fs. Okay, these are the convolutional results. So can give the figure subplot 311 and plot t minus t min and h, and title this is the impulse response, right? ht, x label should be assigned with the time sec, and y label is assigned with the what, the amplitude. Okay, and x lim should be given in the -5 to 10 and grid on. Okay, in the second place we will write to what, the 2 in here t minus t mean u value is in here, and the input signal ut. Okay, and after that we should draw the the output signal, but this output signal should be written with what a t output and y, and this is also the output signal. Okay, and so if I run this code, and then we will have this template pattern for a given what the m, c, k parameters in here. And after that, if we apply the input or unit step signal just like this one, and then we will have this kind of output in here, just like the underdamped system response for a given the mass spring damper system. Okay, so after that we have the 5 value in here just like this one, and after that we apply the 0 value, and in the 0 value we have this diminishing values at the at this signal. Okay, so we can easily analyze the signals based on the the convolutional integral in order to generate our response for a given template pattern, just like this impulse response template. Where is it coming from? It's directly coming from the Dirac delta function, which is applied on the the Laplace transformation of the mass spring damper system. Okay, that's all.